X-rays were discovered in 1895 by Röntgen. Since its discovery, X-rays have been used extensively in medical applications such as CT scan, computer tomography imaging, and in industry for material inspection. Introduction to X-ray spectra. In this lesson, you will learn how X-rays are produced, to interpret X-ray spectra obtained from X-ray tubes, to explain the continuous spectrum and characteristic line spectrum in X-rays, to derive the equation lambda minimum equals Hc over Ev. Click on the cathode. What do you observe? Answer: the fluorescent screen glows brightly. Electrons are emitted from the surface of the heated filament and are accelerated by the high voltage across the X-ray tube. When the electrons strike the target, X-rays are produced. The X-rays hit the screen and cause it to glow. Click the photoelectric effect button. What do you observe? Answer: when electromagnetic radiation of high frequency strikes the metal surface, electrons are emitted. Click the production of X-rays button. What do you observe? Answer: when energetic electrons strike the metal surface, X-rays are produced. Thus, the production of X-rays is the inverse process to the photoelectric effect. Click on the switch. An electron accelerated by a voltage V possesses kinetic energy EV, where E is the charge of the electron. What happens to the kinetic energy of the electron when it strikes the target? Answer: X-rays are produced. About 99% of the kinetic energy of the electron changes into heat in the target, and the rest into X-ray energy. X-rays are often described in terms of their hardness. What is the difference between hard X-rays and soft X-rays? Answer: hard X-rays have higher penetrating power and higher frequencies than soft X-rays. The hardness of X-rays depends on the operating voltage V of the X-ray tube. Click the high voltage button to produce hard X-rays. One of the uses of hard X-rays in industry is to check for cracks in metal components. Click the low voltage button to produce soft X-rays. Soft X-rays are used in hospitals for diagnostic and scanning purposes. Summary: X-rays are produced when high-speed electrons collide with the target atom. Production of X-rays is the inverse process to the photoelectric effect. Hard X-rays have higher penetrating power and higher frequencies than soft X-rays. Click on the switch to produce X-rays. Click the graph button to observe the variation of X-ray intensity I with wavelength lambda. X-ray spectrum typically consists of a continuous spectrum and a series of sharp lines called characteristic X-ray spectrum. The characteristic X-ray spectrum is dependent on the type of target material. Click electrons 1 or 4 and observe their trajectories inside the target. The electrons move midway between atoms. The electrons are slowed down a little by the electron cloud of the atoms and X-rays is produced. Click electron 2. What do you observe? Answer: since the electron is nearer to the atoms, it is slowed down further and X-ray of higher frequency is emitted. Click electron 3. What do you observe? Answer: the electron collides head-on with an atom and loses all of its kinetic energy. X-ray of maximum frequency or minimum wavelength is emitted. Most electrons do not undergo head-on collisions with the atoms of the target material. These electrons are stopped after many deflections. These encounters produce photons of various frequency, thus resulting in a wide range of wavelengths. Hence, a continuous X-ray spectrum or the Bremsstrahlung radiation is produced. Click the incoming electron button to observe a head-on collision of an electron with an atom. Click the derivation button to derive the equation for the minimum wavelength lambda minimum. X-rays are produced in an X-ray tube with an operating voltage of 60 kV. Calculate A. The maximum energy E maximum of the emitted photons. B. The minimum wavelength lambda minimum of the emitted photon. Click the solution button to check your answers. Click the 50 kV button to see the X-ray spectrum produced by a tube operating at 50 kV. Click the 60 kV button to increase the operating voltage. What changes do you observe? Answer: the intensity of all wavelengths increase. Wavelengths of characteristic lines are unchanged and lambda minimum decreases. Click the low button to see the X-ray spectrum produced by a tube with a low filament current. Click the high button to increase the filament current. What changes do you observe? Answer: the intensity for all wavelengths increases. Lambda minimum and the wavelengths of the characteristic lines remains unchanged. Click the K-alpha button to view the collision of an incoming electron with an electron in the innermost shell of an atom. What do you observe? Answer: an electron with high energy collides with and removes an electron from the innermost K shell of the target atom. Thus, a vacancy is created which is filled when an electron from the L shell falls into the K shell, emitting a photon. This produces the K-alpha line in the characteristic spectrum. Click the K-beta button to view how a different line in the characteristic spectrum is created. What do you observe? Answer: when the electron from the innermost K shell is removed, the resulting vacancy may also be filled by an electron from the higher M shell. This results in the emission of a photon, producing the K-beta line of the characteristic spectrum. Observe the X-ray spectrum to compare the intensity of the K-alpha and K-beta lines. Which line is more intense? Answer: the K-alpha line is more intense. This is because the vacancy in the K shell is more likely to be filled by an electron from the nearer L shell. Hence, this process occurs more frequently. The wavelengths of the line spectrum depend on the type of material used as the target. Drag the slider to the right to increase the atomic number of the target material. What do you observe? Answer: the characteristic K-alpha and K-beta lines shift to the left. What can you deduce from your observation? Answer: the wavelengths of the characteristic lines decrease as the atomic number of the target material increases. Summary: X-ray spectrum consists of a continuous spectrum and a series of sharp lines called the characteristic line spectrum. The continuous spectrum is caused by the deceleration of electrons by target atoms. The minimum wavelength in the continuous spectrum is given by lambda minimum equals hc over EV. The characteristic lines are produced when an electron from an outer shell falls to fill up the vacancy created by the removal of an electron in an innermost shell. The wavelengths of the characteristic lines decrease as the atomic number of the target material increases.